Hello, I'm Brian Hurt, and this is Introduction to Type Inference. Got a fair bit of ground to cover, so I'm going to be moving at a certain amount of speed, but by all means, please ask questions. This all makes sense in my head, but the point is to make it make sense in your head. So if you're confused, stop me and let me know. So I want to start with why you care. Why even be bothered with this type inference type stuff? Well, you're at the Haskell Meetup. Haskell is statically typed and type inferred. So it really helps to understand this. It also helps, the basis of this algorithm is also the basis of the type systems for Ocaml, Scala, Swift, etc. A lot of languages are now starting to use these. F# is another one. It is increasingly used in optional type systems. Type bracket, closures, core.typed, C++'s new auto feature that came out, just C++11, I believe, and static analysis tools like Coverity, etc., all use variations of them. So you will be seeing the output of this algorithm in almost no matter where you go. If you don't understand this level of type theory, the more advanced stuff like GADTs and type families, etc., will make no sense whatsoever. And lastly, and probably most importantly, it will help you understand why Haskell is complaining about your code. When writing Haskell, you should probably have a variation of this running in your head all the time so you can be figuring out what Haskell thinks the types are going to be. So when Haskell complains that's not what the types are, you have some idea of what's going on. So an outline of this talk, I'm going to be presenting a subset of Haskell I call SIML, pronounced simple. So it's a very simple language. It's not a language you actually want to program in, but it is complicated enough it lets me get into all of the interesting corner cases, or at least some of the interesting corner cases, and explain some of the more less obvious ideas behind what's going on here. I then actually create a type inference algorithm for it. Actual code will be shown. And I also am going to be concurrently introducing you to the notation used by all the research, known as the natural deduction style. There'll be more on that in a little bit. I will, however, say this is not how GHC actually works. GHC does something significantly more complicated and intelligent than this. But this is a good start for understanding how stuff works. And in the simple cases, how GHC actually does stuff devolves down into what I'm going to be doing here. A little bit of technobabble for those who actually know this stuff. SIML is an enriched Lambda calculus. I enriched it because I don't want to go through the proof that the Lambda calculus is in fact all you need, on which I perform a modified and simplified Hindley-Milner-DeMoss algorithm, at which point I simply reverse the polarity of the neutron flow and pipe the warp core into the deflector shields, and that destabilizes the tachyon field emissions and closes the wormhole. So one of the things I like about Haskell is I can define an entire programming language in code that fits on a single slide. Here is the heart and soul of simple, right? This is the AST. I'm not going to deal with actually parsing this. This is the AST that will be spit out by the parser at the end of the day. And our language, the core of our expression is just, an expression is a constant of some constant type, I'll define in a moment, a variable of some var type, an if, test, on true, on false. This is your standard 3-clause if statement. Function application takes some expression and applies an argument to it. Lambda is our function abstraction algorithm. This creates a closure that takes one argument of whose name is given as a variable and evaluates that expression. a let expression that define local variables, variable name, the value bound to that variable name, and the expression we evaluate with that variable. This works just like normal Haskell or Ocaml. A let rec, this is becoming a little bit Ocaml-ish, but there are type reasons for it I want to demonstrate. A let rec actually takes a list of variables and expressions to bind to them. And the idea here is, with a normal let, this variable is not visible in this expression, it's only visible in this expression. In a let rec, all of the variables defined are visible in all of the expressions, and the last expression, which can see all of them. And last, and interestingly, the typed constructor, which allows me to just take any generic expression and go, it should be this type. So this is how we're actually going to be doing type checking later on, is we can just slap typed on whatever sub-expression we want to give an explicit type to, right? And I'm passing in a type variable around here for reasons I will explain later on. And deriving read, show, EQ, ord, typable, functor, data, etc. See previous talk. I am going to explicitly need functor and foldable for my expressions. The definitions are obvious, so I'm not going to go into them. Functor just says I can map, given a function from A to B and an expression of type, an expression of A, it returns an expression of B. They are auto-derivable. I just wanted to put them on a separate screen. So I should have just auto-derived them. You're correct. And foldable just means I have my standard fold left, fold right functions on it. Works exactly like you would expect. I initially type my variables. This is coming out of the parser. So a variable type is just a string. This is the type for my variable names I've used everywhere else. And for constants, I only have two different types of constants. I have integers and I have booleans. Like I said, this is not a language you actually want to program in, but it's good enough for teaching purposes. Right? The last thing I need to define, or second to last thing I need to define, is what do I mean by a type? This is something we're going to be producing a lot of. So a type is either a Boolean, an integer, a function. This is your arrow type, so it's a function from type A to type B. And I noticed the typo here. These should have A's associated with them. My apologies. Or a type variable. So this allows me to write expressions like it's an A arrow int, or it's a bool arrow, int arrow whatever. And these have the standard instances associated with them as well. Right? The last thing is, this is not really going to come up, I'm just including it for completeness. A statement is our top level statements, which is either a let statement or a let rec statement. So when I finish the parser and actually shove the code out, the parser will actually generate these. But they don't actually show up in the rest of the presentation, so don't worry about them. So the basic intuition, the basic idea behind the algorithm is the structure of the code itself imposes constraints on what type the code produces, on what type the expression has. And we can use these constraints to determine the type. So what do I mean by that? So if I have an expression here that's an if expression, and it's if E1, then E2, else E3, where E1 and E2 and E3 are some arbitrary expressions. I know E1 has type T1, and E2 has type T2, and E3 has type T3. Just knowing this, I can now say, I know that type T1 is of type Boolean, so the test expression has to produce a Boolean. I'm not dealing with truthy values in this language, and you shouldn't either. And type T2 and type T3 have to be the same type. And the type of the if statement is the same type as what T2 and T3 are, right? So just the fact that you have an if tells me some things about the types of the expressions inside the if, simply by it being an if. Does that make sense? Okay. So I want to take the first detour here and start introducing the natural deduction style of logical systems, which if you're going to do anything more with types and type theory and type inference and type checking, you're going to run into this. You're going to open up a paper and you're going to be confronted with a whole bunch of equations that look like they're written in Martian. That's my internal name for this stuff. This is a Martian. This is done for a number of reasons. Hysterical reasons being the biggest one. This is the same notation as used by the mathematical logicians. This is also makes it nice because you can present a whole language of how to type it and how to interpret it in a single page using this sort of notation. But most people here are probably going, "Dear Lord, what does that mean? No human can understand this." So I advise you to take that piece of advice on the front of every copy of the Hitchhiker's Guide to the Galaxy and don't panic. I will explain it. By the end of the talk, hopefully you will be able to look at that and go, I can actually understand that. Or at least I have some hope if I sat down and picked through it, I can understand that. So to start with, the basic form is very simple. There's the two parts. The stuff above the line, if the stuff above the line is true, then the stuff below the line is true. Right? It's a very simple if-then. So I can sit there and I can go, well, if E1 is of type T1, and E2 is of type T2, and E3 is of type T3, and T1 happens to be bool, and T2 happens to be T, and T3 happens to be T, if all of these things are true, then the statement if E1, then E2, else E3 has type T. This is exactly what I was saying the slide before. I'm just using a weirder notation to introduce it. Right? So I want to take a slight philosophical detour here and go, what is meant when I say T1 equals T2, for some types T1 and T2, when I say T1 equals T2, what do I mean by that? So you have the mathematician's definition, which they can go on for years about, but it boils down to substitution. That means I can replace all copies of T1 with T2, and all of my statements remain as true as they were before. True statements remain true, false statements remain false. And I can go the other way. I can replace all instances of T2 with T1, and true statements remain true, and false statements remain false. Right? So if I say T1 equals T, I can just replace all instances of T1 with T. Or if I say T1 is bool, I can just replace all T1 with bool. So I can write the previous statement much simpler by not having all of those unnecessary redundant, T1 equals T, T2 equals T, and T3 equals 3. So this goes, if expression E1 has bool, and expression E2 is T, as type T, and expression E3 is of type T, then if E1, then E2, else E3 has type T. So exactly what I was saying before, just with all of the equivalences flushed through. So that's sort of the mathematician's idea of how things work. As programmers, we have a slightly different meaning. We talk about assignment. And again, assignment is a tricky concept, and there are lots of little subtle variations on it. But at the heart, what it means is when I say T1 equals T2, I mean update the state of the system, change things so that T1 is now T2. The programmer, the mathematician, it's a statement of truth. It's a statement of replaceability. The programmer is going, this is an action to be performed. You can think of it as T1 is some memory location. We're going to write into that memory location. We're going to write into that memory location the value of T2. And that's actually a fairly valid way to think about what we're going to be doing. So keep both of these meanings in mind. I'm going to be switching back and forth between them as we go along. So I want to get started on, so since type equality is assignment in the programmer sense, we need to actually reflect this in our code. So I wanted to introduce you to, there's going to be some monad type match, I call matching here. We're going to actually be doing our assignments, our type assignments inside the monad, inside the matching monad. And I'll define what the matching monad is later. And I'm going to have some function unify that takes two types and makes them the same. It updates the state of the system so that these two types are now the same. Right? So when I say on my slides T1 equals T2, in code that we're going to call unify on T1 and T2 and update and change the state of the system so that T1 and T2 are now the same type. And I'm going to define in code what I mean by that later. The nice thing about defining in code is you can't, I'm cutting out. The nice thing about defining stuff in code is you can't lie. You have to cover all your bases. So our core algorithm is, I'm going to call, our core function is going to be called type infer. And it takes an expression and it returns a computation in matching. That's our monad that lets us do unification. It returns the type that we infer and check for that expression. And that includes, by the way, the possibility of it being a type error of things not checking. So doing a type infer on if now is fairly simple. I'm going to be just spelling out the cases as we go on. So type infer of if of E1, E2, E3. This is our if constructor. How do we do that? Well, the first thing we do is we infer what's the type of E1. Give us the type of E1 recursively. Type infer E2, type infer E3. That gives us our three types here. We know T1 is bool. So we unify, we update the state of the system, and we go, whatever T1 was before, it should be bool now. And then we unify T2 and T3, that's our on true and all on false clauses. And just return the value, whatever unify returns. Unify, remember, unify returns the updated type. This type is the equality of these two types. And what that means will be obvious in a bit. Is this making sense so far? Having not defined half the stuff? So, let's now start on some of your stuff. So here's another one of our formulas, except there's nothing in the above statement. So that means if anything is true, assuming nothing, then the expression true has type of Boolean. And the expression false has type of Boolean, right? We don't need to assume anything to go that. And obviously, 0 has type integer, and 1 has type integer, and da-da-da-da-da, enumerate all of the integers. Let me know when you get done with that. Again, assuming nothing. So the code for this is fairly easy. If our expression is a constant integer, we can simply return tint. It's simply the type integer. And if it's a constant Boolean, we simply return type Boolean. And note, we don't care about what values the integer and the Boolean are. That doesn't change what types they have. Right? Type application is also fairly obvious, although we're getting a little bit more complicated here. So if f has some type t1 arrow t2, note f has to now be a function type. Can't just be, f can't be an integer. And x has type t1, then f of x has type t2. That after we apply the x to the f, it returns the type t2, so the result of the application is t2. Right? So code is a little bit more interesting here. We have the constructor again. Here's our apply constructor. We get the type of f and the type of x here. But note, tf here can be any type whatsoever. So we have to actually match on it. I do an explicit case statement here. It has to be a t function. If it is a t function, then we need to unify t1 and tx. Note, in the mathematics, we could just assume they were the same type. That this only applies if these are already the same type. In the code, we have to actually go make these two types the same type. Call unify, change the state of the system so these two types are the same type. Right? And then return t2. If the type of the function is not a function type, if this comes back like into Boolean, it's a type error. Right? You can't apply an argument to an integer in ML-style programming languages anyways. In other programming languages, they let you get away with stuff like that, but we're not going there. So this is a monad, remember, and all monads have a fail function on them, which I'm taking advantage of, to just simply go fail not a function. For the record, the handling of type errors in this code is absolutely abysmal. If you're doing this for real, you want to do something way more better than it with an error. But that, multiplies the code by some fairly large integer in size. So it didn't happen. So typed expressions are also fairly obvious. So again, if I have an expression x of type t, then if I assert x has the type t, the result of that expression is of type t. Asserting that a given expression has a given type doesn't actually change the type of it produces. Well, actually it sort of does, but I'll get to that. Again, here we can just magically assume as mathematicians that this stuff already has the right type. If it isn't, well, the math doesn't deal with the error case. So our type infer clause for this is again fairly simple. Here is our constructor typed xt. We do a recursive type infer to get to the type of the inner expression. And then we do a unify to make it be the type we want it to be, right? This is, by the way, how you do all of the type checking. All of the places where you would go in the normal language, you have to have an explicit type here. This is how you would handle that case, right? So now let's look at a couple of tricky guys that I want to handle as a pair. Var and let. Now, the problem here is going to be, what is the type of x? For a given variable, what is the type? Here in the let, I know what type I'm going to be assigning to x, because it's going to be whatever the type of E1 is. But I need to pull that into, I need to be able to recover that information down in when I'm typing E2. I'm going to need to recover that information when I actually see that given variable. So up at the let, I know that it's what type it is. Down at the bottom here, down in E2, I need to recover that. So what this means, basically, is I'm going to need to pass around a map of variables and what types I already know they have. Right? So I have to make my type infer a little bit more complex. It has to add an argument. And following the good advice of the previous presentation, I'm adding it at the beginning. It takes, I'm just doing an association list. Again, for simplicity's sake, if you were doing real code, you'd almost certainly want to do a map here, do something fancier here. I'm just doing an association list. So I just pass in an association list of what variables I know of and what types they have. And the rest of the type signature is the same. So here, I now do a type infer. I now have I have the context, which is my list of what types I already know, and a variable. So what I can do is I can look up that variable in the context and go, what type does it have? Well, if I find a type, all well and good. That's what type it has. That's what type the variable has. And if I don't find it, then obviously it's an unknown variable and it's an error and I blow up and die. Let is also very simple in this case. Here I have the passed in context. I pattern match against let. I do the type inference. I do the recursive type inference to find out what's the type of E1 here. And then when I go to do the type infer of E2 here, I add on that the variable x has type T1. So that when I'm down here type inferring E2, and I hit that variable x up here, it'll find the right type. And since I'm always prepending onto the list, and by the way, lookup returns the first value it finds, this means the scoping works correctly. If I have let x equals foo in, let x equals bar in, it will find the nearest, the most internal scope, exactly as you would expect it to work. Right? So this allows me, I have to go back now that I've added the extra parameter, I have to go back and complexify some of the previous examples I did. So when I'm type checking if, I need to pass the context in, add to my recursive type infer. Note, I don't actually care what the context is, I just go, I have to pass it around. And likewise, type inferring for constants and booleans works the same. I can just ignore it. And I'll let you go through the other examples I ran through. It's very obvious. You don't care about the context. You're just passing it around. That make sense? People still following me? So how do we express this in the mathematical notation then, the natural deduction system? It uses gamma, this is a capital gamma here, to represent the context. And the V bar to mean evaluate the right-hand side with the context on the left. So what this means is, with this given context, if given this context, E1 has the type of Boolean, and given that same context, E2 has some type T, and given that context, E3 has some type T, then given that context, the if statement now has type T. So that's exactly what we were, yeah, sorry.
Ryan, I'm sorry to do this to you, but your turnstiles are backwards and it's driving me nuts. I had to say something. the little the V-bar thing, it should be pointing the other way. It should be pointing towards the right.
Did I screw that up? I screwed that up.
It's freaking me out.
I did that just for you. Could have sworn I got that right. Okay. So, where was I? So given this context, the if expression has type T. So how do we, how does var work? How do we do the var? Well, if the given variable has a given type, if that tuple is in our context, this is the set in, then given that context, x has type T. This is just a fancy way of saying we look up x in the context, and that gives us our type for our variable. So this is how we type variables in the mathematics. Likewise, if in a given context E1 has type T1, and if the given context plus the assignment of x has type T1, so I'm extending the context here now. If that implies E2 has type T2, then that context implies that let x equals E1 in E2 has type T2. So this is saying exactly the same thing as the code just a couple of slides ago. I'm just doing it in a fancier way. Do people see how I'm doing that? How the notation works? You can think of gamma as just literally a comma-separated list of variable assignments. And so I'm just adding a new variable assignment onto the end. So this works great for let, where we know the value being bound because it's the value of the expression being bound, and therefore the type. But what about lambda? Now lambda starts being a little bit interesting because we need to know the type of the argument before we can type check the body of the function. And yet it's the body of the function itself that tells us what type the argument needs to be. Right? So I can sit there and I can go, this doesn't actually work in my language, but it works in Haskell. So I can go lambda x goes to x plus 1. And Haskell will go, well, because I'm adding 1 to it, that means x has to be an int. So this whole function, this whole expression has to be of type int arrow int, right? But as we are descending, as we're actually doing the type checking, we're going to see the lambda expression first, and we're going to want to update our context so we can type check the body with what type x has. Because the first thing we're going to do, once we get down to the bottom, is go, okay, what type does x have? Because x is the very first thing we parse here. So we're going to need to give some type to x, but then we're going to, before we know what type it has. And then we're going to have to change it later on as we figure out, oh, what type should that have been? Right? So this gets me, with the math, I can just assume it exists. Magically, pull it out of your hiney, right? So if, with a given context, an x has type T, where x has type T1, if that implies E has type T2, then I can go, with that context, lambda x dot E, that's how the mathematicians do the lambda expression, that has type T1 arrow T2. Of course, you know what type T1 is a priori, right? You can just, psychically deduce it. With code, we can't pull this stunt. So we got to do something a little bit more complicated, a little bit fancier with code. Because I sit here and I start trying to write the code. Type in for, given a context, a lambda x, T1, and what goes here? What should I replace this code with? Once I know what T1 is, I can do a type infer. I can append x comma T1 onto my context, infer E to get to T2. This is my return type. This is the argument type. This is the return type. And that allows me to go, oh, it's a function going from T1 to T2. But what code goes here? Obviously, this doesn't compile with Haskell. or any language, probably. By the way, I want to make one quick comment here. Does this expression look at all familiar to people? I'll give you a hint, don't panic. Just how far we've come. Just wanted to make that. But now we're going to get into a little bit more complicated world, a little bit more complicated stuff, because I need to talk about the two types of type variables, right? The first type is the universal type variable, and this did not come out. The universal type variable. This is the type variable you are all already familiar with. It can represent any type in the whole system. Any type at all, including types that haven't been invented yet. They're also, by the way, known as rigid type variables and Scala type variables. They're trying to kill calling them Scala type variables in GHC in preference to calling them rigid type variables, but I'm told they haven't quite done it yet. So you might still see Scala, and Scala will show up more later. Right? These are exactly the type variables you're familiar with, right? So when I say map has type, takes a function of A to B and a list of A and a list of B, the A and B here, these are universal type variables. They can be any type in the whole universe. The other type of type variable I want to now introduce is what's called an existential type variable. And this is going to be how we cheat our way out of the problem of knowing the type of a variable before we know the type of the variable. And what this means, what the existential type variable means, is this has a type, we just don't know what it is yet. And we're going to fill it in later. It's going to be filled in with some specific other type, but it's going to be filled in later. These are also known, by the way, as flexible type variables, although you won't see that anywhere in GHC. You don't see existential type variables in Haskell for various reasons, but you do see them in other programming languages. Here is an example of existential type variables in Ocaml. So in Ocaml, I can create a reference. This is basically like an IO ref, except it doesn't need to live in IO because it's not a pure language. I can just create a reference none. And this creates a reference that has a _a type, _a option reference. That means it's going, the _a, if you're in Ocaml, all of the underscore types are existential types. That means they're going to get filled in at a later point, but we don't know what they are now because none doesn't tell us enough information to go what type goes here. But if I come along later and I go, assign our set to the reference cell to sum1, and then I go, what's the type of R? It'll go, now I know that _a should have been int all along. And I can go back in time, basically, and update the type. Question?
So would that mean that if you later try to say R equals sum hello, that wouldn't work?
Yes. If you later came along and said R equals sum hello, that would be a type error because you're now trying to unify string and int, and Ocaml knows you can't do that. So you can only update, that is a good point. You can only update the existential variables once. You can only set them once, right? They are just placeholders for, we know that this type is coming, but we don't know what it is yet. So how I keep them straight in my head, and you've been hearing me say it already because this is how I think about it. Universal type variables can be any type in the whole wide world. Existential type variables, that type exists, but we don't know what it is yet. So that's how I keep them straight in my head. That question?
So the phrase existential, you don't mean anything what we usually mean when we say existential in Haskell, right? A type that is not, is erased.
Yeah. No, that is correct. An existential type will be I believe that is correct, that the existential type will be erased at a later point, once you figure out what the type it should be.
Okay, so we're talking about
Yeah. Universal types are generally introduced with for all a dot da 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 da. Existential types are introduced with exists a da 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 da. So if you're actually reading the type papers, it's the difference between the upside down A and the backwards capital E. Does that make sense? Okay. So existential type variables solve our lambda problem because we can simply create an existential variable whenever we want. We can just go, here's a whole brand new existential variable different from every other existential variable in the system, right? And so we can just go T1, allocate an existential variable and call that T1, right? Then we can now do the type infer for the body of the function and just return the type. And I'll show how this works more in a bit. But you see how I'm using it to sort of weasel my way out of this problem case, right? This does require some type signature change. This does require some new functions. I need to type evar, and I'll introduce what that is later. I introduced the type tvar simply to make my data entry easier, which is either a variable, which remember is just a string, so that will be our universal. Our universal types will remain strings, so they'll be the A, B, C, etc. Or it'll either be a universal or it'll be an existential variable of whatever we define our existential variable to be, right? Alloc exist var, to allocate an existential variable, has type matching type tvar, and now you start seeing why I did the type variable on all of my expressions earlier. Unify takes two types with tvar, with our type variables being either universal or existential variables, and returns the unified type. And of course, type infer. Note, type infer, the expression still only takes string variable names. So it takes the variables it takes in, the bindings it takes in, are my tvars are either existential or universal. But the type variables, the expression itself only deals in universal variables. You see how this type signature works? Seeing fewer nods as we go on. Do we have any questions really quick, or quick question?
Just repeat that one more time.
Okay, yeah, I'm doing something a little bit tricky with the types. Notice with type infer, when you pass in the context, that is variables, the types in my context can have either existential or universal variables in them, type variables in them. But the expression itself can only have universally quantified type variables in them. Does that help? Okay. Running out of time, so needing to speed up a little bit. Existential type variables also solve the problem with let rec, because now I can just go through and go, the first thing I do, I'm not going to explain this code a whole heck of a lot. It's fairly obvious if you know the functions. But the first thing I do is I go through and I just assign a new existential variable for each of the values I'm defining in the let rec, which then allows me to run through and type infer all of the variables, what they should be, and then infer the body. So this works exactly like you would expect it to work. Make sense? So, two problems with this that do come up. With typed expressions, the AST gives us type bar, so it only gives us universally quantified type variables, We're not dealing with existential type variables that the user can actually specify. But we need to type tvar, we need to pass type tvar into unify. So AST can only contain universal type variables, but we need to convert that into universal or existential. This is actually fairly easy to do. We simply, this code looks exactly like it was before, except here we just map and go map left says convert all of your universal only type variables into universal or existential variables where they are universal type variables. That makes sense? Second problem is when can universal variables vary? So consider the map function again as our canonical example of using universal type variables in real code. Inside map, as we're writing the code for map, the type variables, map cannot assume what types A and B can be, because they could be anything in the whole universe. But when we call map, if we're in some other function and we call map, they can be whatever types they want. I mean, we can just go, okay, I want to pass in a function of int to float, at which point A becomes int and B becomes float. And we know we need to pass in a list of ints and we get back a list of floats, right? So inside map, the type variables can't vary, but outside map, they can. So how do we handle that? And the answer is actually fairly easy. When you use a variable inside a function that has universally quantified type variables in its type signature, we just automatically convert them to existential type variables. So when we reference map in some other function, it will look up this type and go, oh wait, there are universally quantified variables A and B here. I'll just replace them with existentially qualified variables that I generate so that I can then unify them and go, oh, that means this use of map, A is an int and B is a float. Does that make sense? So the code, I'm going to skip over the code fairly quickly. It's pretty obvious, right? So I just need to do, the first thing is when I'm looking up the variable, the first thing I do is I go through and just get a list of all of the unique variables in my type. And I go map the, I have an error in this code. I should have filtered this. I apologize. So I get a list of the variables. I should just go, I'm only interested in the universally quantified variables, the unique universally quantified variables in the type I just got. I allocate existential variables one for one, and then I simply replace the universal variables with their associated existential variables. Right? So the code's a little bit complicated, but it works pretty much exactly like you think it would. So now I want to go on and start talking a little bit about unify. Unify, remember, is the function that given two types makes them the same. This is only interesting, now we know a little bit more about how unify needs to work. This is only interesting in the case of existential variables, because that's the only place where we can actually change things, right? So a little refresher, we have our data type of what a type is a Boolean, int, a function, or a variable. And unify takes two types and returns an updated type, which is the unification of the two of them in a matching monad. Right? So I can start with the easy cases. If you say make a Boolean type equal to a Boolean type, well, that's trivially, okay, they're equal, there you go. Likewise, make an int like an int. Okay, there you go, they're both ints. right? So if I have the function, if I have the type T1 arrow T2, and I say that is the equivalent of T3 arrow T4, that is the same as saying T1 and T3 are the same type, and T2 and T4 are the same type. I just pair them off and go, the two parts of the function should be equal, right? So again, unify. If I'm unifying two function types, that is simply the unification of the two parts, T1 and T3, and T2 and T4, and I return the composite function, right? Two universal variables only unify if they're the same universal variable. So type variable A unifies with type variable A. It does not unify with type variable B. If I go universal A equals universal B, that is an error. Because A and B could be they could be different types. You don't know they're the same type, right? So unifying two type variables is again simple. If they're the same type variable, they unify happily. If they're anything else, it's a type error, and we fail and blow up. I want to ask one quick interesting question here. I'm not going to answer this because this is ongoing research. What is the scope of a universal type variable? When does one A equal another A or not? The code I've written here, I'll answer the question simply. The code I've written here, universal variables have unlimited scope, universal scope. So every A is equal to every other A and not equal to any other B. But you can start answering the question in different interesting ways. You can start assigning scopes and going, this A is only equal, only equal to other A's in this scope, and it's not equal to A's coming from outside the scope. So there's a bunch of interesting extensions to the Haskell type system that are basically playing games with what is the scope of a type variable. That's all I'm going to say on that subject. Existential types. This is where Unify gets interesting because this is where I can actually change the state of the system. So the rules of unifying existential types are, existential types can only be assigned another type at most once. If an existential type variable has been assigned another type previously, we unify it with that type instead. Otherwise, we assign the other type to the existential type. It is possible to assign one existential type variable to another existential type variable. So we will have to deal with that in our actual code, right? So we need some way to get what the current binding of the existential type variable is. So we need a way to set what the type is. So we have a set evar function that takes an existential variable and what type it should be assigned and updates the system. And we need a way to get whether or not it has a binding, and if so, what. So note, we're returning a maybe type here, not just a type variable. Because if the existential var hasn't been assigned a type, this will return nothing. And again, we're doing it inside matching. Because we're changing the state of the system, so we're doing it in a monad. So the first clause is fairly easy. If the left type is an existential variable, we go, what type does it have? If it's been assigned a type already, been assigned some type T1, so that means previously we did set evar A T1. What we just do is we just literally recurse and we replace our existential type variable with the type that was assigned to it. If there was no type assigned to it, we go, so A now has type T2. Note T2 might actually be another existential type variable, we don't care. Right? And we can do exactly the same thing on the right-hand side. And the nice thing is, by the rules of how Haskell does pattern matching, by the rules that Haskell does pattern matching, it will only fall through here if T1 is not an existential type variable. So we won't go into infinite loops. We pull the exact same stunt here. All other patterns, everything else is a type error. Only the type unifications we have defined are valid. Everything else is type error. Getting told to wrap it up, so I'm going to start skipping over a bunch of stuff. Obviously, this is one implementation. I can do evar is just of type int, and I have some global state. I use a state monad, and I can just do a mapping of types to variables, allocating, update the pointer, setting the evar. The state includes the mapping. Getting the evar, I just look up the mapping. This stuff all works exactly as you think it might. Unfortunately, due to time, I'm going to have to skip Scolamization. So don't worry about this. So we now have a function type infer, which gives us our type inference, which we can use for both type inference and type checking. And as soon as I get a chance, I'll put working code versions of this in GitHub. And hopefully, formulas like this aren't so scary anymore. And you're thinking, hey, I could actually, with a little work, pick that apart and go, what does that mean? So where to go from here? Strongly recommend Types in Programming Languages by Benjamin T. Pierce. This is a book that will introduce you to all of this at much greater detail and much slower pace. It is eminently readable and very easy to understand, or at least I found it such. And then start reading papers. So that's all I have. Thanks.